Now, the final thing is I was going to talk about velocity squared because Gary, I noticed, has a new friend, Toady, who it's hard to know what's going on there. And Toady, expressed the confusion. Why velocity squared? Which Gary has talked about before, but Gary has also talked about why time squared, sure, square feet, but square time, square seconds? No, surely not. But I saw him explaining to Toady that it was really just a matter of when you have time squared, it's really the same as taking distance over seconds, all of that together over seconds. And he was explaining that. But I think the explanation of velocity squared requires another approach. So here's the thing. Remember, velocity equals the change in distance over the change in time, which is another way of saying just distance over time, which is meters per second. It could be miles per hour, whatever. We're going to use meters per second. All right, there's a reason that it's important to remember that it's the delta, and that's basically the reason for that is what if your distance, there's an origin point, and your distance doesn't start at 0? Then delta D isn't going to just be one number. It's going to be one number minus where you started at. Same thing with T. Otherwise, and with unit analysis, you can just think of D versus T, which you can think of as meters per second. All right, so velocity equals d over t. Now, here's the thing. That's all that velocity means. Velocity is a shorthand for distance divided by time. That's it. So, for example, acceleration is the change in velocity over the change in time, right? So that's in unit analysis, v over t. Again, here with the unit analysis, we can just think of, oh, it always starts at point 0. But as you do real equations in the real world, you can't be changing the 0 point. So you want to be able to start a segment of your calculation not at 0. And that's meters per second over seconds, right? So what is the change in velocity, the change in meters per second over a particular time period, right? So if I am every second I'm going 10 miles per hour faster, then after 6 seconds, starting from 0, I'll be going 60 miles per hour, right? And so that is the acceleration, v over t. But look, v is just delta t, or d over t. So that means that it's d over t, which equals d over t squared mathematically. D over d squared. So that's what acceleration is. Now, when you go to the next level, you have force. Force equals ma, right, which would be delta m, but m never changes unless you have a nuclear reaction where mass is changing into energy, so it can actually change. So the change in mass times the change in acceleration, or ma in unit analysis, which equals mass times d over t squared, because there is no such thing as velocity per se. There's distance, there's time, and there's mass, and the relationships between them. A is d over t squared, so F equals m times d over t squared. Now with energy, specifically we'll say kinetic energy, sub k, that equals F times the distance. In other words, you apply a force over a certain distance, not a time. You apply a force over a certain distance, that's what we call the energy, and it ends up as kinetic energy, in this case that we're talking about. So F equals md over t squared times d. Well, any person, I don't want to say idiot, can see that this equals mathematically m times d squared over t squared. Now wait, I'm missing the half. Why is that? The energy is equal to the mass times but there's a half missing. I'm a half off. See, there is no v squared. There's d squared over t squared, which happened for very obvious reasons. Now we're missing a half. Why is the half missing? The half is missing because when you compress a string, the more you compress it, the higher the force. So if you have force times c for compression, it goes like this, right? So F times D is this whole square. F on this side and D on this compression on that side. But wait a second, it's only this part that you want to get. Why? Because that's how much the force is at any amount of compression, so it's 1/2 of it. Here's the square, the triangle is 1/2 of it. So the point is here with the force is not constant with the D. The force of actual depends on 1/2 the D. So you end up with 1/2 FD because it's basically calibrated to springs. But it's the F equals MA part that leads to the T squared. And then since with energy you multiply by D, right? So that's how you get the D squared over T squared. That's why they say V squared. But it's not really V squared, it's D squared over T squared. And with gravity, it is the whole square. Why? Because gravity is constant. A spring, if you compress it halfway, has a certain force. If you compress all the way, it has twice the force. That's the properties of a spring to which these equations were calibrated. But gravity has the same force the whole time. If you have a constant force, then it's FD. But with a spring, it's half of that. And that is to which the kinetic energy was calibrated. And why would there even be a calibration? Well, because of the fact that kinetic energy is this one kind of energy. There's also a latent energy, chemical energy in gasoline, a potential if you burn it. There's also all kinds of potential energy. And the thing is, they all go with V squared. Why? V squared? No, not V squared. D squared over T squared for the mathematical reasons that I've just demonstrated. All right, cheers to everybody.